You're good to go.
Okay, thank you very much, Thomas, for that introduction and for the invitation to give this talk. So the title of my talk is "Strong Cosmic Censorship versus Lambda," and well, strong cosmic censorship as depicted in this first slide, at least in the context of this talk, is really about what happens to observers like the poor fellow depicted here who fall into black holes. And the subject proper of this talk is how does this sort of problem, this conjecture, as we'll see, it's a conjecture due to Roger Penrose, how does it change? How does the story change when lambda, the cosmological constant, is added to the picture? Here's a snippet of Einstein's original paper when he introduced lambda. Okay, so let me begin by giving you a very brief sort of outline of the plan for the lecture. So this subject really begins from a sort of thinking carefully about the differences in the global geometry of the Schwarzschild and Kerr black hole solutions that we all know and love. So I'll begin by giving such a review. And it turns out that it's precisely the difference between Schwarzschild and Kerr that, if you want, gives rise to the strong cosmic censorship conjecture of Penrose. And we'll go through actually several different formulations of this conjecture next. So next, well, it turns out that sort of the underlying mechanism for why this conjecture might be true or might not be true really has to do with competition between what I'll term blue shift and what I'll term dispersion. And I'm going to review sort of the nature of this competition in the lambda equals 0 case. And then finally, we'll get to what I really want to sort of focus on in this talk, the subject proper of this talk, namely what happens to this conjecture when you introduce lambda. And in the sort of, without giving too much of a spoiler, what happens is actually quite surprising. Okay, so this is the plan. So, all right, off we go. Let's begin with this promised review of Schwarzschild and Kerr. So this is Schwarzschild. This is its Penrose diagram, which is very famous, and I'll assume that we all have nodding familiarity with this picture. So what does it actually depict? What are the pertinent properties for the purpose of this talk? Well, first of all, what it depicts is that the singularity R equals 0 is space-like. And this is actually a snippet from a very prophetic paper of J.L. Singh from 1950. So this was actually the first paper to study what's now known as the maximal extension of Schwarzschild, or often called the Kruskal extension. It actually appeared first here in this paper. And this was the first paper, to my knowledge, to ever refer to a singularity in general relativity as being space-like or some other causal property. So this is really an important paper in the subject. So the singularity is space-like, but just because you have a singularity doesn't mean that this necessarily should be thought of as closing off space-time. And in fact, the paper, and this is again taken from this paper, actually asks the question, so it writes, the question may now be raised. Is it conceivable that a test particle should travel right through the singularity at R equals 0? So here we see depicted such a trajectory. So is it conceivable that this could happen? And actually Singh thought that the answer to this question might indeed be yes, but now we actually understand that the answer to this question is a resounding no, and that observers cannot travel right through the singularity because they are eventually torn apart by tidal deformation. And I want to emphasize that this is a much stronger statement than the statement that we all know, and Singh certainly knew very, very well, namely that the curvature blows up at R equals 0. The curvature can blow up without destroying, without tearing apart observers by infinite tidal deformation. So this is a much sort of stronger property, a property which was not known to Singh, although ironically sort of can be shown using techniques that were pioneered by Singh in geometry. And in fact, the first discussion of this issue in these terms, to my knowledge, goes back to the famous textbook, Misner, Thorne, and Wheeler. So this is precisely the subject of section 32.6. So observers are actually torn apart. And of course, this is now a famous fact known to people working in general relativity. So here's this poor observer. Here, he or she goes falling into the black hole. And we see that the observer is eventually torn apart, stretched or compressed, depending on sort of their precise orientation, as they fall into the singularity. Okay, so sort of to summarize, the Schwarzschild singularity is very strong. It really closes off space-time. It tears apart observers. So this is great, but it's somehow slightly inconvenient that, you know, in order to sort of talk about this property, you have to introduce this notion of observers as stick figures. Actually, sort of a precise characterization of this, you know, has to do with the properties of Jacobi fields, etc. So it would be somehow nice if there was another way of characterizing, morally speaking, this property without actually having to talk about observers. And it turns out that there is. And in some sense, what I claim to you is that this property of Schwarzschild, you should really think of it as equivalent to the statement that the metric cannot be extended beyond r equals 0, not just as a twice differentiable metric that follows immediately from the fact that the curvature blows up, but as a continuous Lorentzian metric. Okay? And somehow this difference between, you know, twice differentiable and continuous, this is precisely the difference between merely having curvature blowing up, which in principle might mean nothing for actual sort of macroscopic observers, and observers being torn apart. Okay, so this is really the sort of you can think of this as a dual way to talking about observers, to characterizing how strong the sort of singularity of the metric is. And this is somehow the definitive statement that the Schwarzschild singularity is strong. Okay, so and actually this sounds like a very classical statement, and sort of should have been a classical statement. Actually, it's asserted without proof in Hawking and Ellis, but it was only proven much more recently by Zbirsky in the paper which is cited here in GTG. So to summarize, Schwarzschild r equals 0 singularity is space-like, but is very strong. It closes off the space-time. All observers falling into the black hole reach the singularity and are torn apart in finite time. So in particular, bleak as the future of such observers is, in some sense, it's completely predicted by classical theory. Okay, so that's Schwarzschild. What about Kerr? Well, so when we think about Kerr in the context of this talk, we should always think about Kerr in the context of the Cauchy problem. So the relevant Penrose diagram of Kerr is simply the region which I've depicted here. And what's going on in this picture? Well, from this point of view of the Cauchy problem, the maximal future Cauchy development of Kerr initial data, this is Kerr initial data, okay, is this space-time here. And this space-time is incomplete. So observers that look like this, that have a trajectory like this, only live for finite time. But they're not, it is not incomplete because those observers reach a singularity. No, it is incomplete because the space-time is itself smoothly extendable beyond what's known as a bifurcate Cauchy horizon. So this terminology is originally due to Stephen Hawking, to a larger space-time. Okay, so the larger space-time is not, however, a Cauchy development of initial data. So the larger space-time is not uniquely determined by initial data. In fact, this is a very sort of pernicious example of the feature that somehow incompleteness may have nothing to do with singularity, because in fact, all incomplete geodesics in this space-time, they can safely pass to the extension. So, so let me just say, so a similar phenomenon. So here is a depiction of the observer safely passing to the extension. Okay. So a similar phenomena occurs in the Reisner-Nordström solution of electrovacuum equations, and I may make some references to Reisner-Nordström at some later points in the talk. But the point about this is that in the case of the Kerr solution, the statement of Penrose's celebrated incompleteness theorem, sometimes known as singularity theorem, is not due to singularity formation. So from this point of view, there is no singularity in the Kerr spacetime, in sort of the part of the Kerr spacetime that is uniquely determined by initial data. So Penrose's theorem is telling us that we have loss of uniqueness. Okay, so Penrose's theorem is just telling us that these extensions are not unique, so they are not Cauchy developments. So what's going on here is failure of determinants. So again, to summarize, in Schwarzschild, strong singularity, space-like, all observers falling into the singularity are destroyed. Their future is bleak, but determined. Kerr, no singularity from this point of view. Cauchy horizon, completely smooth. Observers live another day in the extension of space-time, but their future is not determined. So you might think that this sort of second alternative, the alternative of Kerr, is much more favorable than that of Schwarzschild, and certainly is for the observer in question who falls into the black hole. It's much better to live another day and have your future not be predicted than to be torn apart by infinite tidal deformations. But from the point of view of general relativity as a theory, it turns out that there's a sweet justice in the Schwarzschild solution. Exactly because even though you have singularity, and you might think, oh, singularity sort of takes you out of the classical regime, the nature of how there's singularity gives the sort of classical theory a very attractive closure. Because before you're taken out, before the theory leaves the classical regime, classical observers are actually destroyed. So in that sense, there are no classical observers in order to observe the exiting the classical regime. So somehow the Schwarzschild case is actually quite attractive from this point of view. It gives a certain epistemological closure to classical general relativity, whereas what's going on in Kerr is very unattractive because it basically tells us that somehow classical general relativity does not make predictions even for observers that remain thoroughly classical. So this is what gave rise to strong cosmic censorship. And you might think, for now, you should think of the motivation as a little bit of wishful thinking that nature should not be like that. But anyway, it doesn't matter what the motivation for conjecture. Conjecture is conjecture. We can state it and see whether it's true or not. And so Roger Penrose, faced with basically the discussion that we just had, back in 1973, formulated his celebrated strong cosmic censorship conjecture. Let me not talk about the sort of origin of this name. This name was to sort of distinguish this conjecture from a previous version of cosmic censorship, which is now known as weak cosmic censorship. It turns out that neither is weaker or stronger than the other, so the names are a little bit unfortunate, but in any case, they've stuck. And I will not talk about weak cosmic censorship in this talk, so there will be no confusion, hopefully, on account of that. So the conjecture is simply that this Kerr-Cauchy horizon, which is so problematic from the point of view of determinism in theory, is actually a fluke. That's what the conjecture claims. And in what sense is it a fluke? Well, it's a fluke in the sense that, well, Kerr solution, whatever it is, it arose from very special initial data, very symmetric data. It's exactly Kerr. If you had generic asymptotic flat initial data for the vacuum equations, in particular, if you perturb the Kerr data, but much more ambitiously, if you have generic asymptotically flat initial data in the whole moduli space of initial data, then the maximal future Cauchy development, that's the terminology for the part of spacetime that is uniquely determined by the equations, that cannot be extended further. It's inextended. So that's the conjecture. Except if you want to make this reasonably precise, you have to say inextendable as what? And inextendable as what is secretly a way of saying how singular do you want the boundary to be? And well, motivated by the Schwarzschild case, motivated by sort of the good scenario that we saw at the very beginning, you might want to formulate this as saying that it should be extendable in exactly the same way that Schwarzschild was, namely as a manifold with continuous Lorentzian. And again, what does this mean? Morally speaking, this means that observers going to the boundary of space-time, they won't just measure infinite curvature at an instant, which again could be, completely innocuous for the observers if sort of the rate of growth is sort of sufficiently mild. So this statement that I've given here is the statement that, morally speaking, that the observers are themselves torn apart. So this would be a very attractive thing if true, because it would ensure that the strong form of determinism that we saw holds for the Schwarzschild solution is a generic property of general relativity. Okay? It doesn't hold for some sort of solutions of sort of measure zero in moduli space like Kerr, but it sort of holds for the generic solution. So this sort of is the conjecture, at least in its original formulation. Okay, so before I tell you about the status of this conjecture, I have to tell you about another conjecture, which turns out, as we'll see, is related. And this is the stability of the Kerr exterior. So, so unlike strong cosmic censorship, which is a conjecture that has been debated a lot, whether it should be true, is there a reason to think it's true, do we want it to be true, etc. The conjecture that I'm telling you about now, stability of the Kerr exterior, is not a contentious conjecture. It's something that everyone expects to be true, and I can tell you a little bit about its mathematical status very, very quickly. So the conjecture is simply that the Kerr family is stable in the exterior as solutions to the vacuum Einstein equation. So this is the full nonlinear stability of Kerr. So that just means, so if you think about this two-ended picture, that small perturbations of two-ended Kerr initial data leads to a maximal future Cauchy bound. That's the solution that indeed is uniquely predicted by the theory, which has a complete future null infinity. So observers far away observe forever. And such that if you look at the past of future null infinity, so that's this lightly shaded region here, then it's bound to the future by a bifurcate event horizon, which is future complete, and such that in the exterior regions, the solution will settle down to two nearby Kerr solutions, in fact, at inverse polynomial rate. Okay? So that's the conjecture. And actually, this conjecture is very close to being proven in the full sub-extremal range of parameters. So all the sort of ingredients necessary for a proof exist now. And in fact, the Schwarzschild analog of this conjecture, the nonlinear asymptotic stability of Schwarzschild has recently been proven in work of mine with Holzhugel, Rodniansky, and Taylor. And there's a lot of work more generally in sort of the mathematics community in writing up a complete proof of this conjecture. So in any case, this is something that I think very soon will be completely resolved. Okay, so from the point of view of this talk, rarely for a mathematician, card-carrying member of the mathematics community, I'll actually assume the validity of this conjecture and move on. So, so it turns out that if this conjecture is indeed true, so if Kerr is stable in the black hole exterior, then we proved with Jonathan Luke a few years ago that its Penrose diagram is actually globally stable. So its Penrose diagram is globally stable. So again, space-time is bound to the future by a bifurcate null hypersurface. And moreover, the metric will extend at least continuously across Cauchy horizon to a larger space. So, so what this theorem is secretly telling us, or not so secretly, is that, well, observers can still get through the Cauchy horizon even if you perturb Kerr in the full nonlinear theory without being destroyed. So here is the observer again getting through. This is now a perturbation of Kerr. So unfortunately, as a corollary of this statement, then if Kerr is indeed stable in the black hole exterior, again, I emphasize this is not a contentious conjecture. I don't know anyone who doesn't believe that that's true. Then the C0 formulation of strong cosmic censorship is actually false. Okay, so that's the bad news. So we have to sort of go back to the drawing board. So remember, the template for formulating strong cosmic censorship was we want for generic asymptotically flat initial data, the maximal future Cauchy development to be inextendable as something. We just saw that, unfortunately, it's not inextendable in the strongest sense we would have liked, namely just as a Lorentzian manifold with continuous Lorentzian metric. I also claim to you that certain types of statements do not really have good physical interpretation within classical general relativity. For instance, if I said here is inextendable as a C2 Lorentzian manifold, you might think that that's sort of contentful because C2 is curvature is a nice geometric invariant. But actually, if you think more generally about the analog of this statement in the context of other classical PDE of mathematical physics, well, to give you a sort of very concrete example, the Euler equations, the compressible Euler equations of fluid mechanics, then it's very well known, actually since the early 19th century, that smooth solutions develop so-called Schoch singularities. That's exactly the analog of the solution failing to be C2 in sort of this translation to the Einstein equations. And yet the solution continues uniquely as a classical solution with the right so-called entropy conditions. So that's to say, just because something blows up doesn't mean you left the domain of the classical theory. And in fact, everything we know about nonlinear PDE sort of tells us that. So somehow it's manifestly inappropriate to formulate this in terms of, C2 extent. So the question is sort of what might be appropriate given that the strong version is not true. And in some sense, the next best thing I claim to you would be the following statement, that it is extendable as a C0 Lorentzian manifold with locally square integral Christophersons. So it turns out that this conjecture is still compatible with the previous theorem. So my theorem with Luke does not disprove this. And the point about this assumption is that basically this formulation would say that not only can you not extend the metric as a classical solution, as a sort of C2 solution, twice differentiable solution, but you cannot extend the solution even as a weak solution. So this would precisely differentiate this scenario with the analog of Schoch formation for classical PDE, where solutions do extend as weak solutions, and those are known to be physical. So this really would again be saying that there is no sort of physical solution that extends. So in that sense, this conjecture would still say that there is some version of determinism, even though there is still this little question about, okay, well, what do you say about this argument with these sort of stick figure observers that seem to be able to go to the boundary without being destroyed? But anyway, okay, this is second best. So, all right, so this is basically the status of the situation in the lambda equals 0 case. So again, just to review very, very quickly, strong cosmic censorship is the statement that for generic initial data, the spacetime that does uniquely evolve from the initial data should be inextendable as something. Ideally, we would have wanted it to be inextendable as a continuous Lorentzian metric. That would ensure that indeed stick figure observers are torn apart as they approach the boundary of space-time. That unfortunately is not true, at least if you believe in the classical stability of black holes. But it still may be true that solutions are inextendable as weak solutions of the Einstein equation. So this formulation was first proposed by Christodoulou, so I'll call it the Christodoulou formulation. Strong cosmic censorship might still be true. And that's the situation. Okay. So before moving to the lambda not equals 0 case, which again, spoiler alert, is very interesting, I hope to convince you, I want to tell you a little bit about why this conjecture, well, one of the formulations was not true, and why the other formulation might be true for the lambda equals 0 case. And the good news is that whereas these conjectures are really statements about the full nonlinear theory, the mechanism, the relevant mechanism, we can really understand at the linear level. Okay, and it's this sort of tension between blue shift and dispersion. So I want to review sort of this tension in the lambda equals 0 case, because this will then be a basis for understanding what happens when lambda is 0. Okay, so what is sort of the linear version of the problem, which I claim, if you do understand this problem well enough and you're sort of an expert in proving things about nonlinear PDE, you can translate this understanding into an actual theorem about the full nonlinear theory. So what is the linear problem? Okay, so the linear problem, and moreover, I'm going to specialize the linear problem not to the actual linearized Einstein equation, but to the wave equation, which is even simpler, because again, you see all the phenomena here. So in that context, the main problem would be the following: consider the Kerr background. Or if you want to make it even easier, you can look at Reiser-Nordstrom. So this is the Kerr background. This is two-ended initial data. And consider smooth, localized initial data for the wave equation. Okay, so localized, sort of say, compact support or decaying fast in any case as you go to infinity, smooth initial data for the wave equation here. Well, what happens if you evolve this initial data, in particular, what happens in the black hole region, in particular, what happens at the Cauchy rates. So that's sort of, that's the problem. If you can understand this problem well, then I claim you can prove things about the full. Okay. So what are elements that go on in this problem? So what Penrose discovered very early on, in this, in some sense, gave him some support for conjecturing strong cosmic censorship, was the famous blue shift instability. And what is the blue shift instability? Well, it's just the tale of these two observers, the conservative observer who stays outside of the black hole for all time, and the more revolutionary one that decides to fall into the black hole. So as we all learn in our relativity classes, if this observer here sends a signal at constant frequency, as he or she measures it, so let's say every second of his or her proper time, okay, then these signals build up with respect to the proper time of this observer. So in particular, at Cauchy horizon crossing time, oh, you're not seeing the, okay, this has happened before, sorry. I'm going to, so again, if this observer sends a signal at constant frequency as this observer measures it, then the signal builds up with respect to the proper time of this observer here. And so we say that the signal is infinitely blue shifted at Cauchy horizon crossing time. So you might think, because after all, you can think of this as a geometric optics sort of approximation for the wave equation, you might think that this phenomenon should mean that solutions of the wave equation that I described should be badly behaved. They should somehow blow up along this Cauchy horizon. Generic. Okay. So that was sort of the argument. But there is a little catch to that argument, which is that, and let me go sort of back here. If you think a little bit about this argument as I've presented it to you, then, well, this observer sends a signal every second, and the signal has constant strength. Okay. But when considering solutions of the wave equation, I require that the solutions decay at spatial infinity. Okay? So if you look at solutions outside the black hole, so in this region here, that arise from initial data that decay at spatial infinity, okay, then the solutions will also be decaying as you go forward in this direction. Okay? So there's actually some possible tension between the fact that solutions want to disperse in the exterior, they decay, and this blue shift. So it's maybe not clear which one wins a priori. So in any case, the first thing you really have to get a handle on is this dispersion. And indeed, there's a sort of complete understanding of this dispersive phenomenon in Kerr. This goes back to, well, the final word on it was a theorem with Rodniansky and Schlapper-Rothman from 2014. And what it says is that you have decay, which is at least polynomial in rate in this region here. So in particular, along the event horizon, let's say. So you have at least polynomial decay for all solutions of the wave equation that arise from a suitably localized initial data. And I should say that many people have contributed to this problem over the years. In some sense, the first mathematical result on wave equation in black holes was in the Schwarzschild case, and showed boundedness of solutions and is due to Wald and K and Wald. Okay. So anyway, that's sort of the exterior story. So you have this sort of polynomial decay. So you might worry that this polynomial decay might kill the redshift, the blue shift. Sorry. But fortunately, that is not the case. And it's been shown by various people. So Luke and O and Luke Zbierski, and also I have an alternative approach with Chapital and Rothman. So what we showed is that despite this polynomial decay, then for generic such solutions, there is a form of blow up at the Cauchy horizon, namely the local energy of C blows up, the local energy. So if you want to say it in slightly more mathematical language, it's not so relevant for this talk, then we could say that C is inextendable as an H1 log solution across the Cauchy horizon. But this really is just saying that the energy of C measured by a local observer would blow up. All right, so that's good. So in this sense of the word, the blue shift wins. And this is precisely an embodiment of this original heuristics of Penrose. But at the same time, there's something which is quite surprising the first time you see it. And this is another theorem a few years back due to Anne Franzen. And the theorem says that, yes, the energy may blow up, but the amplitude of the solution does not. So Anne's theorem says that under the same assumptions as previous in either Kerr or also Weissman-Rosen, which is of course much easier, then the amplitude, so C itself, remains bounded on the Cauchy horizon. In fact, it is continuously extendable beyond the Cauchy horizon. So that's this theorem, and there are various other contributions following this by Luke Zbierski, Gaich, and Hintz. So now you sort of see what was going on here and why the full nonlinear situation that I described earlier is what it is. So if you think of the linear wave equation as a toy model for the Einstein equations, you should think of C, the amplitude of C is like the metric itself. Okay? Whereas derivatives of C are like Christoffel symbols. So if you naively extrapolate these two theorems to the full nonlinear Einstein equations, then basically what they would say is that the metric itself remains bounded, in fact, continuous at the Cauchy horizon, but derivatives, so the Christoffel symbols, become singular. In fact, they fail to be locally squared. And the remarkable thing is that you can indeed promote at least this theorem here you can promote this statement to a full nonlinear statement about the Einstein vacuum equations without any symmetry in the neighborhood of the Kerr solution. Okay? And this was our theorem with Luke and all, with Luke. Okay. So in summary, just to isolate the sort of the physical phenomenon, in the exterior, we have dispersive effects. These lead to polynomial decay of linear waves. In the interior, we have this blue shift effect. This leads to exponential growth of derivatives. And it turns out that this exponential in whatever coordinates, doesn't matter, eats this polynomial. So this is why derivatives indeed do blow up inside the black hole near the Cauchy horizon. In particular, they blow up so as to fail to be square integrable, right? But nonetheless, this is not strong enough to destroy the amplitude of psi. Okay, so the amplitude of psi remains finite, in fact, continuous. So this is the situation for lambda. Okay, so now we can go to the surprising things that I want to talk about, namely what happens to this story when you turn on lambda of either side. So this is strong cosmic censorship versus lambda problem. So first we all know that Kerr has cousins when you turn on lambda into the Einstein equations, the celebrated Kerr de Sitter and Kerr ADS spacetime. So these metrics were actually first discovered by Brandon Carter, and they take this form here. And if lambda is positive, we call this Kerr de Sitter. And if lambda is negative, we call this Kerr anti-de Sitter. So let me start with the positive case, and let me start with a very, you can think of it as the good news or the bad news, depending on your point of view, but in any case, a very definitive statement. So it turns out that in the lambda greater than 0 case, it's actually easier to prove nonlinear stability results for black holes for various reasons, which I'll in fact make reference to in just a little bit. And so in particular, it has been proven that the Kerr de Sitter family of solutions, at least in the very slowly rotating case, the case where A is very small in comparison to M and lambda, is actually stable non-linearly as a solution to full Einstein equations in the region between the event horizon and what's sometimes known as the cosmological horizon. So this region here is stable in the full nonlinear theory. And actually the reason that it's much easier to prove that it's stable than in the asymptotically flat case is because you actually have exponential decay to the Kerr de Sitter solution. So in particular, along the event horizon, in appropriate coordinates, you have exponential decay to Kerr de Sitter. And the fact that exponential decay is much faster than polynomial decay makes this statement easier to prove. So in particular, the good or the bad news is that our theorem with Luke about this region can actually now be applied. So in our theorem, it was not so relevant whether you had lambda or you didn't have lambda. What was relevant was what assumptions you could make on the event horizon. And somehow the assumptions that you can make in view of this theorem are even stronger than the assumptions that you could make in the asymptotically flat case, given a solution to the stability of the exterior region. So our theorem applies. So in particular, the falsification of the sort of C0 formulation of strong cosmic censorship applies equally well. Okay, so there's no change in that story. But what's interesting in this case is what happens with the Stodulu formulation. That's to say, is it still the case that we should expect that the Cauchy horizon is singular in a weaker sense, and in particular singular enough to prevent extensions beyond the Cauchy horizon as weak solutions of the Einstein equation? So what about the Stodulu formulation? And this is where it gets interesting, because you see, as I said, now in the exterior, you have exponential decay. So now let's think about linear problems. So let's think about just the linear wave equation. So this is my C that I'm talking about here. So now in the exterior, you have exponential decay, governed, if you want, by quasi-normal modes. in the interior, you have exponential growth because of this blue shift. And now it's really a question about numerology. It's really a question of, does this exponential growth trump this exponential decay? Okay, and I looked a little bit just heuristically at this. So again, unfortunately, it's the problem again with the mirror, but hopefully I'll restore it. So I looked at this problem 8 or 9 years ago now, and I looked a little bit about the numerology and on the basis. Actually, it's very naive what I was looking at, but in any case, on the basis of what I saw, I made the following conjecture. Actually, the way I'll phrase it here was really specialized to a nonlinear but symmetric model, but in some sense, at least naively, it's the same story. We'll hear more about this in just a second. So I translated this whole discussion to the Reisner-Nordstrom de Sitter setting, where you could study it in spherical symmetry in a full nonlinear model in spherical symmetry. And what I conjectured is that there's actually a window of opportunity near, but not exactly extremal. So when you're sufficiently near to extremal Reisner-Nordstrom de Sitter, so there's a window, so there's an open set in moduli space of solutions for which the spacetime will have the property that it is extendable as a weak solution in equations. Okay, so basically this conjecture, if true, would say that even Christodoulou's formulation of strong cosmic censorship is false when you turn on positive lambda. So actually, this particular model has been studied by a group in Portugal, Costa, Girau, Notario, and Silva. So this formulation, this conjecture has not been rigorously proven, but they have made progress towards understanding this. So there's a linear version of this conjecture, and the linear version we can think about without any symmetry. So the linear statement is simply the following: consider smooth initial delta posed on a hypersurface here in either Kerr de Sitter or Reisner-Nordstrom de Sitter with parameters sufficiently close but not exactly extremal. Then the solution C of this linear wave equation should extend beyond the Cauchy horizon as a weak solution. So if this is the conjecture I made, and if you believe this conjecture, then that says that Christodoulou's formulation of strong cosmic censorship, at least its linear analog, would be false. And remember that we have now some experience in turning these linear results into non-linear results. So this was my conjecture, and it turns out that in the Reisner-Nordstrom case, there's been recently evidence found in favor of the above conjecture. The evidence is part numerical, but there's also some serious mathematical content to it. And so there's a very nice paper by Cardoso, Costa, Lestunis, Hinz, and Janssen, and there have been lots of subsequent developments following this paper in sort of trying to understand heuristically whether or not this conjecture is true or not. But actually, maybe the most surprising of those developments was about the Kerr case. So it turned out that in the Kerr de Sitter case, then in another paper, which is again numerical, so this is by Diaz, Eperon, Harvey Real, and Jorge Santos. They found evidence that actually in the Kerr de Sitter case, this conjecture is false. And this is surprising because in the lambda equals 0 case, all results about Reisner-Nordstrom were sort of precursors to Kerr results. And essentially, the situation was very, very similar, Reisner-Nordstrom or Kerr. So Reisner-Nordstrom is a very good toy model for Kerr. But here it turns out that if you believe these heuristical results, and we have every reason to believe them, then we see that there's a subtle difference between the Rice-Nordstrom de Sitter and the Kerr de Sitter case, and this has to do with differences in numerology for quasi-normal modes. Okay, so in any case, this is an interesting thing. Of course, this would mean that Christodoulou's version of strong cosmic censorship is saved in the Kerr case, so it's saved, if you want, for the vacuum equations, but this would mean that it still doesn't hold in the electrovacuum case. So now, if you believe that strong cosmic censorship is a fundamental thing, it should not, let's say, be true because we believe that black holes microscopically don't have charge. Not everyone believes that, after all, although that's we're taught reading Hawking and others. But if you really believe that sort of strong cosmic censorship is a fundamental thing, it shouldn't have to depend on accidents of astrophysics. So in particular, this should be worrisome. This statement here should still be worrisome. And it was worrisome to me. And I was wondering if there's yet another way that one can still sort of save this Christodoulou formulation of strong cosmic censorship, which I claim to you is really the only reasonable formulation, given that the C0 formulation does not. And it turns out that there is yet another way out. And this is something that we discovered with Chappell-Rothman. And basically the idea is the following. Since in these formulations of strong cosmic censorship, we're willing to entertain weak solutions which extend beyond the Cauchy horizon, we should also be willing to entertain the same amount of weakness in our initial data. And what we discovered with Chappell-Rothman is that if indeed you consider generic initial data, but not in the smooth class, precisely in this class that you want to entertain as extensions, namely initial data which has locally finite energy, okay, then generic solutions in this class cannot be extended as solutions which have locally finite energy beyond Cauchy. So what this says is that in this sort of weaker class of initial data, okay, so solutions, generic solutions in this class, so remember, these solutions are not smooth, they were never smooth, okay, they're only in this sort of, weaker class, but these solutions, they become less smooth at the Cauchy horizon, and they become less smooth precisely leaving the class of good physical weak solutions. So let me correct something again with the, still cannot see the, okay. All right, sorry about that. So in this sense, by relaxing, by enlarging the class of initial data, you can sort of save, or this suggests that at the linear level that you can save Christodoulou's formulation strong cosmic censorship. And this theorem is very general. It applies subextremal Rice-Nordstrom and subextremal Kerr de Sitter, and it applies for a very funny reason, because in all these solutions, there is a precise relation between the surface gravity of the event horizon and the surface gravity of the Cauchy horizon. And secretly, this theorem just depends on that relation. So it would be very interesting to know whether there is a sort of a hidden, deeper reason that relation always obtains in these solutions. So to summarize sort of this situation, what we see here is that when you have rougher initial data, okay, then exterior dispersion is no longer governed by quasi-normal modes, but it's essentially governed by something related to the redshift factor. And in the interior, the exponential growth of derivatives is something related to the blue shift factor. And it so happens that in the whole subextremal range, there is a relation between the surface gravities, which means that the blue shift factor wins. So, so these ideas and various new ones have been taken up by Diaz, Real, and Santos, and they gave a very nice name to this sort of phenomenon that you have to take the rough with the smooth. Okay? So this is a possible way out, and this is a possible way to save strong cosmic censorship of the Lambda. Okay. But in the last 5 minutes, I really want to talk about what I think is maybe the most surprising and most interesting case of all, and that is the case of negative lambda. So in the case of negative lambda, then, as I said earlier, the cousin of the Kerr solution is the Kerr ADS solution. This is a depiction of the Penrose diagram of the Kerr ADS solution. And then for those of you who know about ADS, you'll recognize here these time-like boundaries at infinity. In view of those time-like boundaries at infinity, then in particular, anytime you talk about dynamics of the Einstein equation or even a linear wave equation, you also have to put boundary conditions at infinity, because the spacetime itself is never globally hyperbolic. It's only sort of globally hyperbolic with sort of boundary conditions at infinity. So there's a way to formulate that. And in this talk in general, anytime I talk about dynamics for the Einstein equations or for linear wave equations in the setting, I'll always be considering reflective boundary conditions. Okay. So, so why should one be very, very worried or alternatively optimistic about this case? Well, so the starting point is always understanding what happens in the exterior. And by the way, for this lambda less than 0 case, I'm only going to talk about linear theory. And well, I'll leave extrapolations to the nonlinear theory to the very end. Okay? So just imagine the study of the linear wave equation on anti-de Sitter or Riser nodes from anti-de Sitter spacetimes. So the first thing that one has to understand is the exterior. And the starting point is this theorem of Holtzegel and Zmielewicz. And what they showed is that solutions arising from smooth localized initial nada, they do decay in the exterior. So these are the exterior regions here. They do decay. But unlike the positive lambda case where they decayed exponentially, unlike the lambda equals 0 case where they decayed polynomially, in the lambda negative case, they only decay inverse logarithmic, only event horizon. Okay, so that's very, very slow decay. And this decay rate is sharp. So the generic solution will only decay like this. And so this really opens the question, well, what does this mean in the interior? Because everything that was proven earlier required that one has at least polynomial decay along the event horizon. And in fact, not only polynomial decay, but polynomial decay at a sufficiently fast rate. So in particular, you might be optimistic that actually in the negative lambda case, this means that psi could actually blow up in amplitude on the horizon. So why do I say optimistic? Well, remember, psi blowing up in amplitude is good if you want the strongest version of strong cosmic censorship to hold. Because again, morally speaking, psi blowing up in amplitude is sort of like the Schwarzschild. This is sort of like the statement that the metric is itself blowing up, not just its derivatives, but the metric itself. So naively, at least extrapolating this statement to the full nonlinear theory would tell you if this happens, then strong cosmic censorship in its original C0 extendability formulation might be true. Okay, so in some sense, this was my hope. Again, to sort of summarize it in this picture, in the exterior, we have very weak dispersive effects, logarithmic decay of psi. So you can consider this, if you know about quasi-normal modes, this weak logarithmic decay is governed by the totality of quasi-normal modes. In fact, it's governed by the fact that there are quasi-normal modes that approach the real axis as the frequency goes to infinity. On the other hand, again, you have this exponential growth of derivatives in the interior associated with blue shift. So the question is which effect wins for the behavior of the amplitude. So I was hopeful that actually, because of the situation, that maybe the amplitude would blow up. But the first result on this problem proved me completely wrong. So this is a result by Kale from a few years back, which considered the Reiser-Nordström anti-de Sitter case. And what Kale showed is that despite everything I told you, despite the fact that you have this very, very slow decay, in the Reiser-Nordström anti-de Sitter case, then you still have exactly the same situation that you had in the lambda greater than 0 and lambda equals 0 case as regards to the amplitude of C, namely the amplitude of C is still bound. Okay, that was disappointing maybe, but then the real surprise came. And that's the situation in the Kerr anti-de Sitter case. So what Kale discovered is the following remarkable property: that in the Kerr anti-de Sitter case, this situation depends on the number theoretic properties of the black hole parameters. And what he shows is that there is a bare generic set of black hole parameters. So that means it's a set which is generic in some very funny topological way. And I'll get back to that in just a second, because this really has to do with number theory, such that if the parameters of the solution belong to that set, then generic solutions of the wave equation on that space-time will blow up at the Cauchy horizon. So what this says is that in this sort of funny bare generic sense, if you extrapolate, then it appears that the C0 formulation of strong cosmic censorship may be true after all for negative lambda. And together with this result, he has a conjecture that says that, well, in the complement of that set of parameters, and it turns out that the complement is also generic. Well, how can it be generic? If you're generic, then the complement should be exception. Well, it's generic in a different sense. It's generic in the so-called Lebesgue sense. So I'll get back to that in just a second when I finish the talk. So this is really the last result here. So for a Lebesgue generic set of parameters, you actually have continuous extendability, just as before. So let me just tell you what happened here. It's very surprising, and then I'll end. So it turns out that the story for negative lambda has nothing to do with the shift. The story is something very different. You see, in the exterior, you have this dispersive effects which are governed by the slow quasi-normal modes. And you only have logarithmic decay. But what's behind this phenomenon is the following. There is a resonance in principle between the quasi-normal spectrum, so the totality of these slowly decaying quasi-normal modes, and an interior scattering pole, which was discovered by Schleppentoch, Rothman, and Kale in a previous work. And the resonance is only turned on if the black hole parameters satisfy a generalized non-Diophantine condition. So that means if the black hole parameters have a certain number theoretical property, then you have this resonance, and this resonance leads to blow up in amplitude of C. Okay. So the blue shift effect, it really only concerns exponential growth of derivatives. Okay, so what happens to the amplitude has nothing to do with the blue shift. So the blue shift effect so the amplitude blow up is because of this mysterious resonance. Okay? And it turns out that this, the parameter satisfying this generalized non-Diophantine condition is generic in the so-called bare sense and non-generic in the Lebesgue sense. And this is actually very reminiscent of small divisor problems in celestial mechanics. So these are exactly the same type of conditions that occur when you try to understand the stability of the solar system in classical mechanics. So anyway, this is a very unexpected thing. There was nothing number theoretical about this problem in the lambda equals 0 and lambda greater than 0 case. And let me just end the talk with this quote from Cayley's thesis. So he writes, surprisingly, small divisors and Diophantine approximation, the villains of the stability of the solar system in Newtonian gravity, may turn out to be the elusive cosmic censor which Penrose was searching for in order to protect determinism in general relativity. So anyway, there's still a lot to say on this problem, because after all, this is really just about the linear case. But if I were to summarize the conclusion of this talk, strong cosmic censorship versus Lambda, I think the jury is still out. Okay, so sorry to have gone over. Let me end. Thanks.
Thanks very much, Mihalis, for this wonderful talk. So we'll take questions. Tony has his hand up already. So Tony, kick it off.
Thanks. Yeah, really nice talk. Really so nicely gone through for something I don't know very much about. So I kind of have two questions really. So the first one is, in these particular cases where the the local energy density does blow up, would we expect in that situation, this in the presence of sort of some UV completion of general relativity, this to excite, say, the stringy modes of the theory, and in which case should we really be playing with general relativity in such a scenario then anyway? And the other question is again related to a kind of like sort of stringy interpretation, which is there's a lot of talk within at least perturbative string theory lately about lambda, and a positive lambda in particular, being sort of in the so-called swampland and not really being part of the solution space of string theory. Might this be what you're seeing here is a sort of yet another symptom of that? So those are my questions.
Yeah. So of course, maybe I should say that obviously this talk has sort of been completely in the domain of classical GR, and one of the attractive things about this question is that somehow you can ask it completely in the domain of classical GR, and moreover, I think if the C0 formulation of strong cosmic censorship is true, this is extremely attractive exactly because it gives you a classical closure. Now, if indeed the C0 formulation is not true, as we know it is not true in the lambda equals 0 case, and sort of the best that we can say is that there are no classical weak solutions, then needless to say, okay, we don't really know what are reasonable sort of notions of classical solutions beyond, sort of the weak solutions. We don't really know. Even for, let's say, weak solutions of other classical PD, we don't really know that these are appropriate solutions of classical generality. So in that sense, it certainly opens the door to questions about, whether, it makes sense to try to understand sort of quantum effects, quantum corrections, whether they will be in play, etc. And yeah, there's nothing I can say, but it certainly certainly makes sense to ask those questions, and there are people who have studied that. In fact, very recently, actually in the lambda greater than 0 context, there's some work of maybe Stefan Hollens and collaborators, I think, which try to understand whether the quantum corrections are sort of stronger than the sort of the classical singularity, so they can allow you. This is at a semi-classical level, but so whether they change the story. So I mean, one can certainly study that, and has been studied. On the other hand, it's also important to keep in mind that one of the attractive things about this problem is that it can be studied classically, and the status of classical theory is, of course, much more secure than the status of any sort of quantum extension. So, somehow anything that any definitive statement that one can say at the classical level is somehow always preferred. So your other question was about whether sort of the fact that something is not true, let's say for positive lambda, you know, is there any hidden reason for that, which is coming from some, you know, if I interpret it correctly? Well, I don't know. I mean, sort of, it's, you know, all these results, both in the positive lambda and the negative lambda case, for different reasons, they have to do with numerology. So in the positive lambda, the reason that this phenomenon happens, where it happens, in, you know, that window near externality, really has to do with sort of the precise numerology. And sort of in the negative lambda case, what's going on here is even more bizarre, and you know, it has to do with this sort of very funny number theory. You know, okay, so certainly from the classical point of view, all these things are just accidental. These are solutions. You know, we have this whole family of solutions. They admit, you know, things which have this numerology, and if you have this numerology, you get these effects. Now, is there some hidden reason for that? Which maybe, but certainly nothing I can see. Okay,
thank you.
So, Mihaly, if I may ask a question, apart from the hidden reason, I mean, what is for me a little bit perturbing, perhaps, about the potential dependence on the asymptotics, right? Is that to this problem is that I'd feel a lot more comfortable if somehow, you know, you could forget the asymptotics or make some much more generic assumption about this, because of course, I mean, then I start thinking about things like, okay, what if I had 5 black holes in the universe? And what if, you know, what about all the matter in the universe and all of this stuff? So can I ignore all of that and only think of the 0 lambda, positive lambda, negative lambda? Or do I still then start worrying about everything that is in the exterior, basically, in the properties of the exterior?
Well, I mean,
region.
In principle, you have to worry about everything that's in the exterior. Now, in some sense, hopefully, if you believe in, you know, the asymptotic flat assumption in general, if you believe that, you know, this is a reasonable mathematization of isolated self-gravitating systems, even though, okay, we know that there's sort of, you know, a lot of other stuff out there. So, yeah, I mean, to the extent that you believe that that is a good mathematical model, then, okay, you can sort of believe, you know, some.
I mean, the thing is, this is quantitative, right? I believe that in a sense that if I do certain calculations and I stick in a very small lambda with you know, sometimes depending on the sign, sometimes it doesn't depend on the calculation, then I can actually argue quantitatively that all of these corrections are very small and they don't affect my result. So
yeah, but
I'm not sure I can do it here.
These statements are also quantitative in the fact that, okay, any sort of, you know, you can interpret sort of, if you want to introduce error bars on your, you know, asymptotically flat approximation, or on lambda, on, you know, your agnosticism on the value of lambda, or on anything like that, then again, in principle, you can still make sort of statements that says that, you know, up until a certain time, this picture applies. Okay. And then it's only when you try to go beyond that time. And in any case, what you'll see is that in particular, already at that time, what these results tell you is non-trivial, in the sense that the differences at that time are non-trivial. So for instance, the fact that, you know, in the lambda equals 0 case, the Cauchy horizon is stable from, you know, this C0 point of view. Well, of course, again, if you don't know that you actually have asymptotic flatness, but you only have asymptotic flatness up to whatever, then you can only say that, you know, the Cauchy horizon is stable up to, you know, some time. But already, if you look at that time, you will see a very, very different picture than, let's say, the Schwarzschild picture. Yeah. So, you know, needless to say, in trying to interpret any of these results in the real world, you know, you'll always face these type of, at least if you want to really interpret them literally, you'll always face these type of caveats. But the claim is that they are still sort of distinguishing things quantitatively in a very meaningful way. Okay. So yeah, that's sort of the most conservative thing that one can say. But you're completely right. I mean, that sort of, you know, this is really telling you that sort of, these results are very sensitive. Finally, they're very sensitive. And yes, sort of given, the fact that, there is a sense in which this is a very rough, saying asymptotically flat, etc. Vacuum asymptotically flat. It's a very rough.
No, yeah, I mean, I'm wondering about this in the sense that Tony said it, in the sense of effective field theory and and quantum fields and all that sort of stuff. To which extent, actually, this could, in principle, have.
Well, of course. In general, I think there's, when discussing obviously quantum effects, then there's another layer of uncertainty that we don't know. But just say let's be very conservative and just say, the good old astrophysics that we do in principle, know, and we certainly know that it's there.
Sure, yeah.
Yeah, so it is a reasonable question to ask. And I think in any case, it certainly, I would also be interested in that sort of, understanding more, going beyond what I just said. So, okay. Now make a more precise sort of model for, atmospheres of black holes and so forth, whatnot. And then, okay, try to understand, does it actually not make a difference, or does it? I think it's a good point.
Okay, I'll move to Jorma, who also has his hand up patiently for a while now.
Hello, thank you, very enjoyable. One question about your theorem with Rothman, 2018, with this non-smooth initial data. So your theorem was for generic initial data in that non-smooth class.
Yes.
Could you elaborate on this notion of generic in this case?
Yeah.
For example, if I had initial data that is smooth in some open set, would that be automatically non-generic for you?
Yes. Although, of course, I should add that, there are different classes that you could so there are different classes that you could consider, but maybe so first of all, for the purpose of complete disclosure, because this is linear, then sort of to show that for the generic solution, it suffices to show that for one solution, okay? Because that means that this gives you genericity in the sense of this tells you that in a well-defined sense, the sort of the bad solutions are at least codimension 1 in moduli space. So secretly, all we do is we show that we can construct a solution in that class with that property. Okay. So anyway, that solution. So anyway, there actually we know several different constructions of such a solution, and certainly some of those constructions are smooth in most places, but that's not. Okay. I don't think that's once you're not smooth somewhere, then in some sense you should think that okay, you're not. There's no physical reason that you should be smooth here and not there. So it's as if you're not smooth anyway. So that, so in some sense it is a, anyway, it's a funny property. It's a slightly funny paper. But we do affirm that it does, that it is reasonable simply because, okay, the whole question in the first place was one of excluding solutions which might have been weak. Because again, if you want to exclude stronger solutions, then you need a weaker, they are excluded. So the whole point was excluding such weak extensions. So the argument was simply, well, okay, you might as well, if you want to exclude such weak extensions on the basis that they are physical, then, well, they should have been physical also as data. And if you look at the generic solution in that class where, okay, we're using this fact that sort of you can immediately translate, there exists one solution to statements about generic solutions with this interpretation, then anyway, I should also say maybe, so I didn't talk at all about weak cosmic censorship, but there is a precedent to sort of relaxing the regularity assumptions on initial data as a way of making it easier to prove versions of weak cosmic censorship, which again goes back to work of Christodoulou, where he proved weak cosmic censorship in the setting of spherically symmetric scalar field collapse. So this was restricted to spherical symmetry, but fully nonlinear for the Einstein scalar field system. And it turned out that, you know, sort of if it's still an open problem to prove, even in that restricted setting, weak cosmic censorship in the smooth class. So if you look at smooth initial data and you want genericity in smooth initial data. But what he showed is by relaxing a little bit the assumptions on initial data, so allowing initial data, which are not smooth, but still for which you have well-posed initial value problems, so you can treat them as sort of classical solutions, then you could prove weak cosmic censorship. And the advantage that having this less regularity gave you is that certain physical mechanisms were clearer. They operated more clear on such solutions. And in that sense, philosophically, it's sort of similar here, that when you relax from smooth solutions, asymptotics is really governed by numerology of quasi-normal modes. And there are many funny things that go into that numerology. Whereas for this sort of more general class of solutions, then the asymptotics is governed by something else. And the something else is more robust. So anyway, there is a precedent for that, but okay, needless to say, you know, we put that out there, but okay, I certainly, you know, I don't claim that it's definitive. And I think it is very interesting that there is a difference. It seems that there is a difference to the, you know, the validity of the conjectures changes when you change the class of initial data. So not just the class of extensions, but the class of initial data. Yeah, it is what it is.
Okay, so I don't see any other hands, and we're already at 4:22. So I think at this stage we're going to thank Mihalis again. Thanks very much, Mihalis, for this very nice and interesting talk. It was a pleasure having you, and next time hopefully we'll have you in person.
Yeah, I hope to visit soon.
Okay. Bye-bye, Mihalis. Have a good afternoon. Thanks, everybody.
Bye, everybody.